The change in electrical potential energy per unit charge is defined as electrical potential difference, or electrical potential, or voltage, and can be described by this. Delta V is equal to delta E over Q. Now this is very, very important that you notice that this is delta E with no arrow over top of it. So what does it represent? Energy, okay? So important, okay? And the Q for this one is the charge in coulombs. This is the charge that's inside the field, or it's the one that's experiencing the field. That's how we think of this one, okay? So be very meticulous about writing out your E's with an arrow or E's without an arrow, etc. Potential difference is a scalar quantity. Small amounts of energy can also be measured in units of electron volts, which is EV, okay? So, however, joules are the SI units for energy, so all calculations involving energy and formulas need to be done in joules. So this is really, really important to remember about, because you'll be asked questions where you'll be given EV, and you need to know how to convert it to joules. This is in your data booklet.
So if you're getting EV, you just multiply 1.69 by 2.
Yes. So for this, if we are to convert this into joules, you have your 2.10 EV times by 1.6 times 10 to the negative 19 joules over 1 EV. Okay, then we can cross out our EVs, and you get 3.36 times 10 to the negative 19 joules. Or you could set it up differently. I'll show you the way that I like to set up. Like, really what you need to look at when you're setting it up is that you need to cross off your units, right? So if you put your EV on the bottom, it will cross off here. The way I like to set up these questions is I do it kind of like I make two fractions. It's the same calculation. I just like to do it like this. 1 EV per every 1.6 times 10 to the negative 19 joules is equal to 2.10 EV x joules, and then I solve for x. I just like writing it as fractions. It helps me. It's the same calculation. I just prefer to set up a fraction that I say 1 EV for every this amount of joules is equal to this amount of EV for the joules. It's the same thing. I like to do it that way, so I was just going to tell you guys how I do it. Okay, so since the electrical potential energy is changing between a set of parallel plates based on, bless you, electrostatic repulsion and attraction, the electrical potential, so this is delta V, is also changing, even though the electric field remains uniform. Okay, so if this plate is positive, and this plate is negative, I'm going to do kind of color code this. I'm going to draw my electrical field, so that's going to the negative. It stays the same everywhere. It is uniform. Let's draw our battery in. Now, let's say I hook up a battery that is 100 volts. I'm going to use green. So, that means that from the positive to negative, the potential electrical difference between those two is 100. So what I'm going to do is say, okay, at this side, it's like there's 100 and 0. So between here and here, if I'm looking at an object that, say, at this distance, it has 100 volts of electrical potential difference. But what if I look right here to here? It has less potential difference because it's farther down. Okay? So let's say like that one's like 75 volts. Say I'm halfway now. Halfway would be 50 volts. And then the last quarter is 25 volts. So the electrical potential remains uniform, but at different places in between the plates, the electrical potential can be different. The potential, because they're at different distances. Okay, this is like one concept. Now I'm going to give you a whole different type of concept for the fields. And it's really important, again, that you keep your E's organized. So like E without the arrow and E with the arrow. So flip your page over now.